Rahim. My name is Kainat Abasi and my roll number is 16TE83. This is the lecture number 13, that is week 9 of digital signal processing. In this lecture, we will revise the concept of fast Fourier transform and inverse fast Fourier transform. If we are given, let's start with fast Fourier transform. If we are given a sequence x of n is 1, minus 1, 2, 0, 1, minus 1, 1 and 3, and write it in binary form 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. We will split this sequence into 4 segments, even and odd indexes, and it will give 1, 2, 1, 1 and minus 1, 0, minus 1, 3, that is 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0. These are the indexes for even and these are for odd. And then we will again split it into 2 segments using even and odd indexes, and we will get 1, 1, 2, 1, minus 1, minus 1, 0 and 3. Now apply 2-point DFT. In 2-point DFT, we will divide our circle into 2 parts, that is 0 and pi. At 0 we will get 1 and at pi we will get minus 1. And we will draw a figure like a butterfly using this concept. This is 1 and this is minus 1, and same is for all that. And the answer we get is 2, 0, 3, 1, minus 2, 0, 3, minus 3. And the formula we used is x of k is equal to E of n plus W 0 2, that is circle is divided into 2 parts, 0 2 and 2 0 and 2 1. This is always 2 0 and this is 2 1 into odd index. Now apply 4-point DFT to the result we obtained, minus 2, 0, 3 and minus 3. In 4-point DFT, we will divide our circle into 4 parts, 0, pi, pi by 2 and minus pi by 2. And the results we obtain are this. Note one thing, in DFT or fast Fourier transform, we will move clockwise in the circle. Now make the same figure. And by moving clockwise we will get 1, minus j, minus 1 and j. And after the multiplications, the result we get are 5, minus j, minus 1 and j. Similarly 1, 3j, minus 5j, minus 5 and minus 3j. This is 4-point DFT. Now apply 8-point DFT to the result. In 8-point DFT, we will divide our circle into 8 parts. And the figure is like this. Remember one thing, even index came as it is and odd indexes are always multiplied with the values of circle. Divide the circle into 8 parts and the values we get are 1, minus j, minus 1j. Similarly 0.707 plus j of 0.707. Here minus 0.707 minus j of 0.707. 0.707 minus j of 0.707, and here the real part is negative plus j of 0.707. Move clockwise in the circle, that is 1, 0.707 minus j of 0.707 minus j, and so on up till 0.707 plus j of 0.707, and the results we obtain using 8-point DFT are 6 minus 2.121 plus j of 1.121 plus 2 minus 1 plus 5j plus 2.121 plus j of 3.121, then 4 minus 2.121 minus j of 3.121, 1 minus 5j, and 2.121 minus j of 1.121. I will rewrite the sequence here that I obtained 2.121 plus j of 1.121 minus 1 plus 5j minus 2.121 plus j of 3.121, 4 minus 2.121 minus j of 3.121 minus 1 minus 5j, and 2.121 minus 5j of 1.121. This sequence is known as fast Fourier transform, and the sequence is x of k. If we want to recover x of n from x of k, we will perform inverse fast Fourier transform. We will divide this sequence into 4 segments, then into 2 segments, like we did above, into even and odd indexes. And then in inverse fast Fourier transform, we will move anti-clockwise in the circle. That is, if for 4-point segment, 4-point inverse discrete Fourier transform, the circle is 1 minus j minus 1 and plus j. In inverse Fourier transform, we will move anti-clockwise. This is the only difference between fast Fourier transform and inverse Fourier transform, and we will recover the sequence. By doing all the calculation, we will get the following sequence: 8 minus 8, 16, 0, minus 8, 8, and 24. And you can see this sequence is not the same as the original x of n, but if we divide the whole sequence by 8, we will get original x of n, that is 1 minus 1, 2, 0, minus 1, 1, and 3. In this way, we can recover our signal x of k to x of n. That is, using fast Fourier transform, if we apply fast Fourier transform of x of n, we will get x of k, and if we will apply inverse fast Fourier transform on x of k, we will get x of n. Now one more concept, that is, if sampling frequency f of s is equal to 20 kilohertz, we can find the frequency resolution f of s divided by n, which is equal to 20k divided by 8, that is 2.5k, and the maximum frequency fm is equal to f of s divided by 2, which is equal to 10k, that is pi frequency or normalized frequency. If we want to eliminate frequencies lower than 4000 Hz, what we will do? In the x of k sequence, we will put x of 1, x of 2, and x of 7 equal to 0. Why we are putting x of 7 is equal to 0? Because x of 7 is the conjugate of x of 1, x of 2, and we will get a sequence By eliminating lower frequencies, the differences are more. In this way, you can eliminate the lowest frequencies. Hope you will find this video helpful. Thank you very much.